Okay, so the second video in electric fields is Coulombs Law. Shouldn't take us too long. We're just going to quickly talk about Coulombs Law. Coulombs Law is concerned with the force that charged objects exert on each other. So really we're just going to look at what affects this and define and maybe do a quick example of using Coulombs Law. So Coulombs Law came about 1785. He came up with a law that describes the force between two charged objects. Now the most important thing to remember is that it is an inverse square law. Just in case you have forgotten what we mean by an inverse square law, you may have seen this before in lessons. If you look at the paint gun in the middle of the sort of this sphere here, what this is getting you to think about is imagine spraying paint using a spray gun, and what you're looking at is the area that the paint goes on and how thick it is. So if you imagine if you sprayed from this point and you measured at a distance of 1 metre, which is on this particular circle here, the amount of paint, it would all hit this 1 unit of area. So we'd have, let's say for example, 1 millimetre thick, and that paint would just be over 1 area unit. If we move out now to 2 metres, you can see that because we've doubled the distance, if you drew out the squares, the areas of unit, the unit areas that it would go over, it would sort of double in both directions. So instead of having 1 unit, you'd end up with 2 by 2 or 4 units. And those 4 units would have the same amount of paint that was here. So basically that paint would be, the 1 millimetre paint would be spread out over 4. So you'd only end up with 1/4 of a millimetre thickness of paint, and so on. So really by doubling the distance, you would, if you double the distance, you end up sort of quartering the amount of paint. So if you go from 1 metre to 2 metre, you end up going from 1 millimetre thick to 1/4 millimetre thick. So by doubling the distance, you're increasing the area by 4 times, which is quartering the thickness of the paint. So this is the most important concept in electric fields, and also gravitational ones, is the fact that the field strength is inversely proportional to the separation of the objects. So as we're going to talk in a second about increasing the distance, then as you increase the distance, the field strength would reduce. So if we're thinking about the force between objects, the force between objects should start to reduce using the inverse square law. So this was the law. We've sort of seen that the force is inversely proportional to the square of the distance. So force is proportional to 1 over r squared, and really it's fairly logical to assume that the force is going to be proportional to the charge of each object. So Q1, Q2, here's 2 charges. The bigger these charges are, then the greater the force, but the bigger the distance are, the smaller the force. If we put all this together and we insert a constant of proportionality, which is K in our case here, that F equals K, Q1, Q2 over r squared. If you've looked at gravitational fields, this is pretty similar to F equals G, M1, M2 all over r squared. A little bit more on this constant then. What would be the value of K? Well, to find K out, what you could do, if you put 2 known charges, Q1, Q2, in a vacuum separated at a particular distance, measure the force between them, you could rearrange this formula to have K equals FR squared over Q1, Q2. If you did that very sensitively, you come up with a range of values to get a value for K. And this can be done. This is what Coulomb did, and he came up with a value that K is equal to 9 times 10 to the 9 metres per farad. Farad's the unit of capacitance, which you may have met. You could work out the units by looking at the base units of F r squared over Q1, Q2. If you converted that down to the SI units, you could work out that the units for the constant K are metres per farad. Just try and remember them if you can. The most important point here to note is that this is the largest value of K possible. If you put any material between the charges, then this is going to affect how the field permeates, if you like, through that material. So with a vacuum there, then this is going to be the largest value of K possible. So for a vacuum, we write that K is equal to 1 over 4 pi epsilon naught. So this epsilon naught is known as the permittivity of free space. The units for epsilon naught are farads per metre, because if you think about it, we've done, this is K is equal to 1 over epsilon naught. So whatever the units for K were, the units of epsilon naught are going to be the reverse of that. So K was meters per farad. Epsilon naught is going to be farads per meter. So some people remember this value of K, but you are given on the formula sheet epsilon naught, so you can always work out the value of K by doing 1 over 4 pi epsilon naught. So there is Coulomb's law in full, that F equals Q1 Q2 over 4 pi epsilon naught r squared. So on the exam formula sheet you are given it in this format. Some little points to consider about Coulomb's law. The force can be attractive or repulsive. If you've got two positive charges, they're going to repel. Two negatives will repel. A positive and a negative will attract. It's best to use, I always find it's best to use the formula to come up with the magnitude of the force and then look at the signs of the charges to work out the direction and whether it's going to be an attractive or repulsive. So if you look at the signs of the interacting charges, it's a little bit more obvious. The electric force between two charged objects absolutely dwarfs the gravitational force. If you might have done this in lesson, but if you don't believe it, then calculate the force between, say, a proton and electron, and the force between a proton and electron in terms of their masses, just by using the equivalent gravitational force, and you will find that the electrostatic force absolutely dwarfs the gravitational. And as we've said, if there's an insulating material between the charges, then the value of epsilon will change. It will decrease as epsilon 0 is in a vacuum. Some quick questions then. Two spheres A and B have a charge of plus Q each. They're separated by a distance r. There is a repulsive force between them. F, what happens to F when the charge on A doubles? Well, the two spheres A and B, they've both got positive. So if we put A and B in here, and if we double A, so we double Q1, then you can see that force is going to be doubled, so our F should be 2 times F. If the charge on both spheres is doubled, then Q1 and Q2 are both doubled. So when you multiply two things together that have been doubled, the result that you get is 4 times. So F becomes 4 times. If you keep the charges the same, but this time you double R, then notice that the R is squared. This is an inverse square. So if you double R, then you're sort of doubling something and squaring it, which is a factor of 4, but you're dividing by, because r squared is below the line, so the force will reduce by a factor of 4, so it'll be quartered. Calculate the electrostatic force between an electron and, first of all, a proton at 2.5 times 10 to the minus 9 metres. So here you've just got to put your charge in as minus 1.6 times 10 to the minus 19 and plus 1.6 times 10 to the minus 19. Multiply those out and then divide that by 4 pi, our constant, and the distance between them, which is 2.5 times 10 to the minus 9 metres. If you do all that, you should get an answer of about 3.7 times 10 to the minus 11. And the second part of this question, the electrostatic force between an electron and a nucleus of a nitrogen atom which has got a charge of plus 7, again doing exactly the same. So this time your two charges are minus 1.6 times 10 to the minus 19, and multiply that by 7 times 1.6 times 10 to the minus 19, and you've got your distance there, 2.5 times 10 to the minus 9, and you get a slightly bigger force. And in these cases, if you imagine it's an electron and a proton, it's a positive and a negative in both cases, so these forces will be an attractive force.